Hi everyone, my name is Christine Schuknecht. I'm a master's student at the University of Ottawa in Canada, and I'm talking today about quantum private broadcasting. This is based on a paper on the arXiv, published with my co-authors Dr. Anne Broadbent from the University of Ottawa and Dr. Carlos Gonzalez-Guillen from the Universidad Politecnica de Madrid in Spain. So what is private broadcasting? This is when you have one message you want to send to multiple recipients. You want to broadcast this message to multiple people. Now, what kind of channel do you want to use to send this message? Well, we're going to assume our message is sensitive and that it needs to be protected. So you might not want to use a carrier pigeon as your communication channel. And it's safe to assume that there might be someone who's listening in to this channel. So there might be an eavesdropper who might intercept your message. Since it's sensitive, we don't want them to know what you're sending, so we're going to encrypt our message so that if they intercept it, they won't be able to tell what we're sending. Classically, this private broadcasting problem is easily overcome because we can just copy the messages as many times as we want, and we can encrypt each copy with the same encryption key, and there won't be any issues with that. So if we look at the one-time pad as an example, we can make T copies of our message M, encrypt each copy with the same key, K, and then we end up with T copies of the same ciphertext, C. And each ciphertext has the same information theoretic security as just one copy of the ciphertext. So what this means is we can encrypt with the same key each copy, and it doesn't counteract the security properties of the ciphertext here. So that's classical private broadcasting. What is quantum private broadcasting? Well, this is when we have a pure quantum state as our message, and we're assuming there's no contact between our recipients. So you can think of this as a globe where each of the pinpricks are your recipients that you want to send your message to. So they could be anywhere in the world and there's no contact between them. So we have a message we want to send to T people, and we're requiring independent decryption. So what that means is that each person who receives an encryption message, they should be able to locally decrypt without having to interact with anyone else. And this results in a specific encryption structure, which we can see in this picture here. So we have T copies of our quantum state. We're encrypting all of them with a unitary matrix. We send it to the recipient, and they can locally decrypt with the conjugate transpose of the encryption matrix. And they're back with the original quantum state again. Notice how we don't have a large unitary matrix as our encrypting matrix, because if that was the case, then each recipient would have to interact with each other to be able to locally decrypt, and we don't want that. We want no contact required between our recipients. So that's what I mean by a specific encryption structure. So with quantum private broadcasting, we have defined security and correctness with this new concept, and we have something we call a delta correct T recipient quantum private broadcast, which we call TQPB. So we have an encrypting map and a decrypting map. So with our encrypting map, both of them rely on the key K, and this H sub M is our message Hilbert space, H sub C is our ciphertext Hilbert space. Notice our input for our encrypting map is the T copies of the message that we're sending, hence the tensor product T to our ciphertext tensor product T. But we only care about local decryption, so decrypting is just HC to HM. So with delta correct TQPB, we have this norm here that we want to satisfy. So our encrypting map composed with our T copies of our decrypting map, and we are restricting to the symmetric subspace. Now the symmetric subspace, as seen down here, is we have a quantum state in the Hilbert space HD of T copies, so tensor T, and we have the property that when this PD of pi is applied to this quantum state, we end up back with the same quantum state for pi in the symmetric group of T elements. So that's all the permutations of T elements. What this is really saying is that when you permute your quantum state T times, like T permutations, you're ending back with the same quantum state. And with this restriction to the symmetric subspace, we're saying that our inputs to our encrypting and decrypting maps, they need to be in the symmetric subspace. So this encryption decryption, we are looking at the difference between this and the identity in the symmetric subspace. And so this diamond norm here, we want less than or equal to 1 minus delta. And when this inequality is equal to 0, that's what we call a perfectly correct quantum private broadcast. So that is correctness. We also have security, which we have with epsilon indistinguishable ciphertext. So we have this angled sigma here. So the sigma is a general density operator, which is fixed, and this is a state replacement channel. So what happens is if you apply this state replacement channel to another density operator, you end up back with sigma again with the trace of that density operator. So we look at the average encryption minus this fixed state replacement channel. Again, we are restricting our input to the symmetric subspace. And looking at the one-to-one norm, which is the max of the trace norm, we want this less than or equal to epsilon. And that's what we call epsilon indistinguishable ciphertext. And we can also take into account adversaries with side information by changing this norm to the diamond norm, because the diamond norm can take into account auxiliary spaces that could be entangled with our message space. Again, we want this less than or equal to epsilon. And in either of these cases, if the norm is equal to 0, that's what we call perfectly secure T-recipient quantum private broadcasts. So that is quantum private broadcasting. What do we want to do with this? Well, we want to find secure encryption schemes that can be used for T-recipient quantum private broadcasting. And we consider 3 solutions, and we focus on the key length in each of these solutions in terms of the classical bits. So we look at the number of unitaries needed for the encryption scheme. Then we take the logarithm base 2 to find out how many classical bits would be needed, and that's how we compare our 3 solutions here. So let's start with the quantum one-time pad, which hopefully we are familiar with. This is the poly operators X and Z in the identity, such that when you have the average encryption, it ends up with a output that's independent of your original input. That is quantum one-time pad, normally used once, but we have T recipients. Can we use the same encryption key for each copy that we're encrypting, like we could with the classical one-time pad? Well, let's look at 2 copies, see what happens. We can look at a double quantum one-time pad here. So the encrypting key is just the AB. Notice how it's AB for both copies of row here. And if we cleverly choose an example where we have row 0 as 2 copies of the 0 state, and row 1 is 2 copies of the plus state here, if you look at the average encryption of the double quantum one-time pad for each of these states here, we end up having this inequality happening here where we have the average encryption of the double quantum one-time pad minus the fixed state replacement channel being greater than or equal to 1/2. Remember how I said if it's equal to 0, then we have perfectly secure TQPB, but since we have this greater than or equal to 1/2, we can't have a perfectly secure 2QPB here. We don't want that. We want something that's perfectly secure. So what can we do? We could use separate encryption keys for each copy that we're sending to our T recipients. The problem is that the number of unitaries needed is exponential in T, like 4 to the power T here. So when we take the logarithm, we end up with something that's linearly increasing in T. So as T is increasing, our key length is going to increase linearly. We ask ourselves, can we do better than linear in T? The answer is yes, we can, if we look at unitary T designs. What are unitary T designs, you may ask? Well, they're finite sets of unitary matrices along with a probability distribution such that when you average over your design, you end up with the integral over the whole unitary group with respect to the Haar measure. And what this means is that when you take a unitary from your design, it's going to appear Haar random when you apply it up to T times. And this is good because we want to have random unitaries for our encryption keys and our encryption schemes, but randomness is expensive. So if we can have something that saves on the cost of randomness, but still looks random, that's what we want to use. So this is kind of the definition for unitary T designs here, where our small k is our encryption key, the big K is the set of all keys, the P of UK is the probability the unitary is chosen from the design, and we have this equal to the integral over the whole unitary group with respect to the Haar measure. And this integral here is tended to be called the T twirling channel, where this row here is just a general density operator. So this is unitary T designs. Are they secure as TQPB schemes? Well, we need to look at it and see. So let's look at a example with adversaries against side information. So we start with a quantum state that has the auxiliary space and the symmetric subspace here. And we can use Schmidt decomposition to make it into the summation here, where this A sub I are orthonormal states on our auxiliary space. This phi sub I are orthonormal states for our symmetric subspace, which gives us the density operator here. Now, since we're using designs as our encryption scheme, we can make the connection between the average encryption and the T twirling channel. And we can actually rewrite this T twirling channel as this equation here, where this first part is looking at the symmetric subspace, and this part over here are subspaces orthogonal to the symmetric subspace. So this pi sim is the projector in the symmetric subspace. This tau sim is the normalized projector in the symmetric subspace. And this b just denotes subspaces orthogonal to the symmetric subspace, where pi b is again the projector and tau b is the normalized projector. So this T twirling channel is like our encryption right now. So that is going to be applied to the symmetric part of our density operator up here. And since these are in the symmetric subspace, when they're replaced down here where we have rho, this whole part over here with the subspaces orthogonal to the symmetric subspace is going to go to 0. Because when you have projectors orthogonal to the symmetric subspace applying to symmetric elements, you end up with 0. So this whole part of our equation just goes to 0. And what we're left with is just this first part here. And this trace can be written as the inner product, which means our I and j's are only going to appear when I is equal to j. And this collapses down to just tau sim here. And what this means is that our average encrypted output for unitary T designs as encryption schemes will look the same. It'll just be this tau sim, regardless of the auxiliary space. And what this means is that we have security against side information because regardless of the auxiliary space, our encrypted plaintext is going to look the same. Notice how we had our input in the symmetric subspace, right? That was part of our definition for our TQPB schemes. You might ask yourself, why does it have to be in the symmetric subspace? Well, let's consider if it's not in the symmetric subspace. So for example, if we had rho 0 here, this is a density operator that, as you can see, it's permutationally invariant. If you permute these tensor products here, you're going to have the same rho 0. And consider, say, rho 1 is just your normalized projector in the symmetric subspace. If you look at the encrypted output for both of these entries, you're going to get something that's, they're not going to equal each other. So we're not going to have a one-to-one norm that is equal to 0. We can't have a perfectly secure TQPB scheme when our entry is not in the symmetric subspace. So that's why we have to restrict our input to being in the symmetric subspace. So those are unitary T designs. What about our key length? That's what we want to compare. So we need to look at the bounds for unitary T designs. So there are lower and upper bounds for weighted and unweighted unitary T designs, which are basically polynomial with respect to T. So in terms of our key length, we're taking the logarithm of the bounds here, so it'll be logarithmic with respect to T. So if we had an example of just D being 2, so qubits, we have the logarithm here of a polynomial with respect to T. Now this logarithmically in respect to T is better than linearly in respect to T, which was the quantum one-time pad. So this is better, but we're still not satisfied. Can we do better than even this? And the answer is yes, we can, if we have something new that we call symmetric unitary T designs. And these symmetric unitary T designs are relaxation of unitary T designs that mimic the action of the Haar measure in the symmetric subspace. So when you look at the definition of symmetric unitary T designs, they look very similar to unitary T designs, with the difference that your input has to be from the symmetric subspace. For unitary T designs, our input rho could be any general density operator. For symmetric unitary T designs, it has to be from the symmetric subspace, hence symmetric unitary T designs. And the security of these symmetric T designs as TQPB schemes, we can just use the argument that we had for unitary T designs, because the argument that we just went through uses the fact that the input is from the symmetric subspace, which is what we have for symmetric unitary T designs. So it automatically comes over to being secure as a TQPB scheme for symmetric unitary T designs. Since this is something new, we need to somehow have bounds for these unitary T designs. How many unitaries will we need for such a design? Well, we have exact and approximate upper and lower bounds that we go through. So for the exact lower bounds, when you have a symmetric unitary T design, you can actually view this as a one design in USIM, so like the symmetric subspace, because if you view the symmetric subspace as a total Hilbert space, this USIM is just the unitaries that are acting in that Hilbert space. And so you have a unitary, T tensored times, and it's acting in the symmetric subspace, and you can just view that as another unitary, just one unitary acting in the symmetric subspace, which is how we get the comparison with one designs in the symmetric subspace. And since it's a one design, we can use the upper bounds from one designs to hit a lower bound for symmetric one designs. And instead of the dimension d that's used in the general bounds, we now have dsim, which is the dimension in the symmetric subspace. And we have a resulting lower bound of dsim squared. So that's lower bounds. What about upper bounds? Well, if you have a symmetric unitary T design, if you view it as a linear operator, it's going to be an element of the convex hull of this set A. So it's going to be convex combinations of the elements in this set, where again, we're restricting our unitaries acting on the symmetric subspace. Clearly, this convex hull of A is going to be a subset of the convex hull of B, where this V is again acting in USIM, but it doesn't necessarily need the tensor product structure that U has above an A. And we actually know the dimension of this span of B because it will have the same dimension as the set of homogeneous polynomials of degree 1 in the entries of V and V bar. And this dimension was calculated by Rory and Scott in 2009. And since we have this dimension, we can now apply Carathéodory's theorem to say that the elements of the convex hull of A can be written as the convex combinations of at most the dimension of B plus 1 elements. So we end up with dsim to the power 4 minus 2dsim squared plus 3, where Rory and Scott's result was the plus 2. And so since applying Carathéodory's theorem, we have the now plus 3. So this is going to be a polynomial with respect to dsim, which means our key length will be logarithmic with respect to dsim because we're taking the logarithm base 2, which is end up going to be logarithmic in t because dsim is also polynomial with respect to t, but it's actually a smaller polynomial than what we had for unitary T designs. For approximate bounds, we do have lower and upper bounds that we derive in our paper, which I'm not going to go through. If you're interested, feel free to check out the paper on the archive. Essentially, we look at previous results in approximate bounds and just apply them nicely to our symmetric unitary T designs. If you're not fully convinced with my arguments that symmetric unitary T designs are the best of these three options, let me try and further convince you with this toy example here. So we're letting D be 2, so we're looking at Q bits, and we're letting T vary. So this quantum one-time pad key length is linear as we expect. The T designs and symmetric T designs are logarithmically increasing. And you can see here that when T is greater than 5, our symmetric designs have a smaller key length than our quantum one-time pad. Meanwhile, it takes T being greater than 7 for the regular weighted unitary T designs to have a smaller key length than the quantum one-time pad. So what this is kind of showing us is that when T is small, so say you're sending your message to only 2 or 3 people, you could just use independent keys with the quantum one-time pad, and that would be fine because that's kind of the smallest key length here from these 3 options. But when T is getting bigger, it would be more prudent to use the symmetric unitary T designs as your encryption scheme because you'll have a smaller key length, assuming that that is what you are concerned about with your encryption schemes. We left open further applications of symmetric unitary T designs. So can these new symmetric designs be used for something other than TQPB? We don't know. Hopefully, we left that open. We also left open the relaxation of the correctness of the TQPB problem. So all of the applications we talk about in our paper assumes perfect correctness. We left open whether relaxing that correctness would result in a better key length for the solutions that we've considered. And lastly, we also left open whether there exists another solution to the T-recipient quantum private broadcasting that has the same security and similar key length to our solutions, but with fewer restrictions. So maybe you don't need to restrict the symmetric subspace with another solution to this T quantum private broadcasting problem. We left that open. That is all for me. Thank you so much for listening. Thank you to my co-authors for all the work that they've done with this paper. And if you're interested, feel free to check out the archive. Thank you so much. Have a great day.